So this is about a power series as the sum of a geometric series. So previously we've been talking about writing out terms of a series using this notation where you have the original function, so like f of c, and then the next term is the derivative times x minus c wherever it's centered. Remember, then you go to the second derivative, x minus c squared over 2 factorial. And as you go on out, you could say it's going to be as n goes from 0 to infinity. So it's the nth derivative at c, depending on how far you go, right? Then you'll have x minus c to the n all over n factorial. And so you had to go through a lot of tedious work. You would take the first derivative, the second derivative, the third derivative, plug in your number wherever it's centered, and then, write all this out. So what we're talking about today is kind of a shortcut for some certain functions that you're given. It doesn't work for all of them, but it works for some of them. So first of all, we need to take a quick look at geometric. Again, we talked about that several days ago. Remember, geometric series are formed by multiplying by a common ratio. So you start at a particular number. So like in this first case, it says, let's start at 2. And then in order to get the next term, you multiply by a particular number. They're telling me the ratio is 3. So the next number would be 6. And then you keep multiplying by 3 every time in order to get the next term. So the next term would be 6 times 3 or 18. And then 18 times 3 is 54. And you could keep going on out. And the general term is going to be a, which is 2, and then your r to the n, so 3 to the n. And that looks like a geometric series. If we want to, we could say the sum as n goes from 0 to infinity of a times r to the n, right? That's geometric. Okay, on the second one, this time I'm going to start at 2, but if I multiply by negative 3, so my next term is going to be negative 6, and then times negative 3, positive 18, times negative 3, negative 54. And hopefully you can tell now the only difference is that it's alternating, which makes sense, because if you have 2 times negative 3 to the n, that negative is going to force it to be positive first and then negative, and then alternate depending on if n is even or odd. And if we want to, we could say the sum as n goes from 0 to infinity of 2 times negative 3 to the n. Remember, this is your a and your r to the n, because that's how we write geometric. Okay, well, what if we look at it not as just numeric? What if we look at the common ratio as being x? So if I start at 1, my first term is 1, and then if I multiply by x every time, my next one would be x, and if I multiply that by x, I'm going to have x squared, and if I multiply that by x, I'm going to have x cubed, and I could keep going out. And if I think of this as a geometric, I could say the sum as n goes from 0 to infinity. Remember, a times r to the n, so it would be like 1 times r to the n. And no, of course, you don't have to write that 1, but I just wanted you to see the a and the r to the n. And so this time it becomes a polynomial, right? Because of the fact that our common ratio was x. Okay, well, remember how we said that the sum of a geometric series is a over 1 minus r. So this series, the sum of this series is going to be a over 1 minus r. So what we've essentially just said is this series is the same as, it's equivalent to 1 over 1 minus x. So this is the function that gives us this series. So if I can identify a function as looking in like this format, if it looks like an a over 1 minus r, I can think of it as geometric. So for example, if I'm told that my function is 1 over 1 minus x squared, well, that kind of looks like an a over 1 minus r. If a were 1 and if r were x squared, then it's exactly what it would be, right? It would be that function. So remember, a is your first term, r is your common ratio. So if I multiply by x squared, I'm going to get x squared. And if I multiply by x squared again, I'm going to get x to the 4th. And if I multiply by x squared again, I'm going to get x to the 6th. And notice the directions say find the first 4 non-zero terms and the general term. Well, there's my first four non-zero terms. And my general term, the sum as n goes from 0 to infinity. Well, if I'm thinking of this as geometric, isn't it a times r to the n? So a, which is 1, and then r to the n. And if I want, I could think of that as the sum as n goes from 0 to infinity of x to the 2n. So essentially, I've written the series for this function, but I didn't have to go through finding, f prime of x, and then the second derivative at x, and then the third derivative at x, and then plugging 0 in for all of them, and then using that formula up at the top. I just made it look like the sum of a geometric series. Okay, so the key is you have to get it to look like this. So the a can be anything on top, right? But the denominator, it has to be a 1 at the beginning, because the formula for the sum, look right here, is 1 minus r in the denominator. Well, when I look at the next example, I have an a on top, that's fine. On the bottom, I have an x, and the fact that it's a plus doesn't matter, right? Because I know in my formula up here it's a minus, but I could always think of it as minus a negative x. So that's not a problem. But I don't want a 4. That 4 has to be a 1. So what we could do is we could manipulate this a little bit. And in the denominator, if I were to take out a common factor of 4, then do you see the first term right here would be a 1? Unfortunately, this is not the factoring that we're used to doing, but factoring is just like dividing, right? If I take out a common factor of 4, that first term is 4 divided by 4, which is 1. And that second term is going to be x over 4. So you can always check and make sure you're doing it right, because if you were to distribute that 4, would you end up with 4 plus x? Yeah, you would. So now you're like, okay, well, I have this number out in front of my 1 minus r. Well, think of that 4 as being in the numerator, so it would be like a 1/4 over 1 plus x over r. Oops, not x over r, sorry about that, x over 4. So now it fits the pattern. My a is 1/4, and my r is negative x over 4, because remember we want 1 minus. So I'm going to think of it as 1 minus negative x over 4. And so I can write my series. My first term is 1/4. If I multiply by negative x over r, it's going to become negative x over 16. And if I multiply again by negative x over 4, it's going to become positive x squared over, let's see, 16 times 4 is 64. And if I go one more time, it's going to be negative x cubed over 64 times 4, I believe, is 256. So there's my first 4 non-zero terms. And then the general term, sum as n goes from 0 to infinity. So it's a, which is 1/4, times r to the n. Okay? I would say most of the time you'll see them like our first example. Okay? Sometimes they'll take it to the level of the second example, but it would be pretty rare for them to go to the level of this third example. Okay? For this third example, what makes this one a little bit higher difficulty is because it's centered at x equals 2, which means all of my terms, I don't just want x's, but I want x minus 2, right? Remember how up in our original formula up here, that c is where it's centered, right? And we have x minus c. On the ones that we did right here, it was centered at 0. So there was no x minus c because it was just kind of x minus 0. So that means I need my r to have an x minus 2 in it. Okay, I need my r to have an x minus 2 so that I can multiply by x minus 2 every time. So I need to think of this as something over, and I might have, something plus or minus, it doesn't matter. And then in this second term, I need it to have an x minus 2, not just an x. There might be a number in front or a number on the bottom, but I need it to have an x minus 2 so that I can say my r has an x minus 2 in it. Okay, So I need to think about how that compares to what I have here in the denominator. Well, right now I have a 2x. I don't just have a single x. Well, if there were a 2 right here, then, and I distribute, that would be a 2x. So definitely I have a 2x. But the problem is, if I were to distribute, that would be a 2x minus 4 in the denominator, right? Well, I don't want a 2x minus 4. I want 2x minus 1. So what number could I put over here at the beginning that would combine with that negative 4, which would be equivalent to a negative 1? Well, I think if I were to put a 3 here, now check that denominator. 3 plus 2 times x minus 2. Is that equivalent to the denominator that I started with of 2x minus 1? I think it is, right? And so you might be saying, okay, well, how does this help me? Well, at least now I have an a on the top for now. That might change. And then I have a something. It's not a 1. I really want that right there to be a 1. And it doesn't matter if it's plus or minus. And then all of this is my r, right? And I was making a point of making sure that my r had an x minus 2 in it. Okay, well, but I don't want that to be a 3. I want it to be a 1. Well, how did I handle that up above? If I wanted that first term right here to be a 1, didn't we just factor that number out? So I'll leave the 15 on the top. In the denominator, I'm going to factor out a 3. Remember, factoring is just like dividing. So if I take the 3 out of the first 3, I have 1 plus, and if I take a 3 out of that second term, it's just like dividing. I actually have 2 times x minus 2 all over 3. Okay, so I don't really want that 3 on the bottom, so I'll put it on the top. So at the top, I have like a 15 over 3. So I have 5 over 1 plus 2 times x minus 2 over 3. Now I know it's ugly, but at least it's in the form of a geometric, right? So my a is 5, and my r is this entire thing right here of 2 times x minus 2 over 3. So in geometric, we always start with the a. So my a is 5 plus, now I multiply that times my r. So it's going to be 5 times 2 times x minus 2 over 3. And then my next term, I multiply that again. So isn't it just going to be 5 times 2 times x minus 2 over 3 squared, because I'm multiplying by that whole thing, and I could do the same thing and keep multiplying. So my general term is going to be n goes from 0 to infinity of a, which is 5, times r, which is 2 times x minus 2 over 3 to the n. Okay? Like I said, the majority of what we see is like the first two examples, but you know, there's a slight chance that we might see something like this third example, so I thought it was worth kind of going through and showing you. All right, so homework, this 9.8b, I believe it's two pages, and then of course the answers are on page 314.